Yesterday, we talked about synthesis. How do we know a synthesis reaction? One product, right? It could be more than just two reactants. Typically, we're going to see probably two, either two compounds or two elements, and they produce one product. That's how you know for sure. We also talked about decomposition. How do you identify decomposition? One reactant. It's the opposite of synthesis. So those two kind of go hand in hand. Again, flashcards are going to be your best friend. Highly encourage you guys to make those. Now we're going to talk about single replacement. You may also see the term single displacement. Okay? They mean the same thing. One piece is going to be replaced by another piece. So our generic equation here looks like this. A plus bx yields ax plus b. So what we've got when we talk about single replacement is we have an element plus a compound, and now we have a new compound and a new element. All right? So on your flashcard, I would write single replacement or single displacement. Write my general formula. You're looking for a single element. Now, how can elements ever be written when they are by themselves? Can they ever have subscripts when they're by themselves as a single element? Can they? Brinkelhoff, right? That's exactly what I'm getting at here. Brinkelhoff. You should, again, jot it down on every test and quiz so that you remember those 7 diatomics. When they are by themselves, they have a subscript of 2. They are still considered to be an element, folks. Not a compound, because that's all it is one element. It's not mixed together or bonded to another element. That's our basic definition, our basic chemistry of what a compound is. All right? So this is what it kind of looks like. We're going to write a few examples down. The ones that you guys did in lab looked like this. We had zinc plus HCl. All right? Now, when we take a look at single displacement or single replacement, every time that we look at one of those reactions, we have to look at what's called the activity series. So you need to get your reference packets out and flip to Table J. All right, Table J. The element that is by itself, the single one, he's going to come in and try to kick out the like element in the compound. So in this case, zinc is a what? It's a metal, which is also a cation, right? Metals tend to lose their electrons, so they form cations. What's going to be my cation in my compound of HCl? Hydrogen. How do we know it's hydrogen? Because it acts like a metal, but how else do we know it when it's in a compound? Cations always come first. So, zinc is going to try to come in and kick out hydrogen. But before we can just go ahead and write it out, we've got to look at the activity series. All right, and this is what Table J shows. We've got 2 activity series, actually. We've got one for metals and we have one for nonmetals. Take a look at the nonmetals. What's similar about all of those elements? They're all Brinkelhoffs. Okay. What else is similar about them? Look at your periodic table.
They're all gases.
They're all nonmetals. They're all gases. Well, at room temperature, 2 of those aren't gases. What else are they? Take a look at
Group 17.
Group 17, which are known as the... They're all halogens, guys. So really, it's kind of like the halogen activity series. Those are the only 4 you need to worry about. Side note. All right, so how this activity series works is that the element that is by itself, that's trying to come in and kick out something else, has to be more active. So the elements that we had with our example, we had zinc is trying to kick out hydrogen. So find where those are on your activity series. Zinc is here, kind of in the middle. Hydrogen is down below. Is zinc more active or less active? More active. So will this reaction take place? Absolutely. Now, our new piece is going to be zinc chloride plus hydrogen gas. Balance that equation. What's going to be my coefficients here? 2HCl, is that it? Yeah, that's it.
Oh, yeah.
That's all we need. Yeah, look at that. So, like Zach said, anytime an element that is part of Brinkelhoff, one of these 7 right here, is by itself. So in this case, hydrogen is by itself. When it's not bonded to anything else, it's got a subscript 2. Notice chlorine. Chlorine had a 1 over here. It has a 2 right here. It's something we're going to talk more about in our second period today, is when we predict products. Okay? Those ones may have a 2. Even though they're Brinkelhoff, they may or may not. It depends on what they're bonded to. It had a 1 over here because hydrogen has a +1 charge. Okay, so it balances out that way. It's got a 2 here because zinc has a 2+ charge, so we need 2 chlorines. That goes back to our naming and bonding rules that we've already done. Brinkelhoff, guys, is only when they're by themselves. All right, and they exist as a single element. Let's jot down another example. This one is going to look like this. It's going to be sodium plus water, and it's going to produce sodium hydroxide plus hydrogen gas. Go ahead and balance that equation. Guys, so if you're struggling, I'm not saying this was you. I know you're waking up, okay? I know. But my point here, guys, is when you see water, write it as HOH. This is going to be a whole lot easier to balance this equation if you show the 2 ions that go into water. Now it's going to be a whole lot easier because look at your metals. Sodium are balanced. Hydroxide, I've got 1 and 1. Hydrogen, right, isolated by itself, I've got 1 on the left and I've got 2 on the right. So I need to put a 2 here. Well, what else does that change? It changes my hydroxides. So then I have to change my sodiums as well. So it's 2, 2, 2, 1 is what you would have. If you're struggling and you have water in your formula, I highly recommend writing it as HOH. Okay? Just a little trick of the trade that may help you out. Now, what I forgot to do before this, will this reaction even take place? What do I mean by that? For this reaction to take place, what do we have to look at? The activity series. So sodium is trying to come in and kick out hydrogen. Well, let's go over here. I'm going to erase the ones that I had before, at least zinc. So hydrogen we know is down to the bottom. Where's sodium? Yeah, is it more active? Absolutely. So every time you've got a single replacement reaction, folks, you've got to use table J to see if it's more or less reactive. If it's more, the element that's by itself trying to come in and kick them out, if it's more reactive, or active I should say, it's going to work. If it's less active, it's not going to work, and all you would write is no reaction. Right? The analogy that I kind of use here is, think about, like, you ever seen Back to the Future? Right? You know when they're at the Enchantment Under the Sea dance? Okay, I don't know how it is, with dances these days or not, but do people cut in anymore? No? When you're dancing? Well, you know what I'm talking about, Back to the Future, if you've seen it, right? How there's like, I'm cutting in, McFly. All right? That's kind of what's going on here. Okay, I know it's a kind of a weird, obscure analogy. It's like when you're cutting in to kick somebody else out to take their partner. All right? Keep track of that. We're moving on to double replacement reactions. So the other one was a single replacement where one element came in and switched with the one that was like it. Now here with double replacement or double displacement, we have the ions. Notice that's a key word. Ions. Double replacement reactions often exist as ions. When we do solubility in February, okay, we will do a whole lab with double replacement reactions. We do what are called net ionic equations with solubility rules. All right, so we will come back and do reactions with that. The one that you guys did in lab, what happened with that reaction? Remember from the other day, the double replacement reaction that you guys did, what happened? We used the potassium iodide and the lead nitrate.
Oh, it turned yellow.
It turned yellow, right? As soon as you dropped one drop in there, it immediately turned yellow. Okay? What's happening is we had ions, meaning we had two soluble compounds, and once we mixed them together, something became insoluble. What does insoluble mean, do you think? Can't dissolve, so what state of matter would it be now? It's going to be a solid. If you were to actually go back to the waste bucket in the back, you could actually see the solid particles resting on the bottom of that from that reaction. This is what it looks like. AX plus BY yields AY plus BX. So how I encourage my students to think about this is what we're going to do is we're going to switch partners. So the analogy I used, do you guys still do this? I know we had to do this in gym class back when I was in school, and it was the most awkward, awful thing. Especially it was like middle school. So it was like 7th, 8th grade. Square dancing. You guys still do that these days?
We did in 6th grade.
No, right? Super awkward. And I don't know why they always did it at the most awkward time. We only ever did it in 7th and 8th grade. We didn't do it beyond that. I don't know why, but it's the most awkward time. And I can remember my gym teacher this day is like, hey, find a partner, get in line. We're like, looking around, you know. He's like, all right. He had like 30 seconds he gave us. And he's like, you, and you. Starts getting all mad and stuff. But what do you do in square dancing? You dance. Yeah, a ton of stuff. You do what, though, with your partner? Do you have the same partner? Who is square danced? You switch partners. So my whole analogy, the whole story, you know, that I'm still scarred by from middle school gym class. Thank you, Mr. Young. Switching partners, okay? That's exactly what we're doing here. Notice where A goes. A goes with Y. X goes with B. This is kind of like your FOIL method in math class. Remember that? Yes? No? Outsides go together, insides go together. That's exactly what's going on here. A now was with X, it becomes with Y, and then B goes with X. Notice, though, what letters are first over here on the right? A and B. Where were they in the first two compounds? They were first as well. Why is that? Cations always come first. Jot this down in your notes. Remember, cations always come first. Cations always come first. Don't forget that when we start predicting products, which we're going to start doing that a little bit next period. Often, one of the new compounds will be a PPT, a precipitate. What is a precipitate? It's a solid, yeah. And you think about it because it does drop out of solution. So it's a solid will form. It's exactly what happens. So we're going to write that reaction here as an example. It's one of the classic ones. All right, we've got potassium iodide plus lead 2 nitrate. Okay. Now, let's take a look at this. Who's going to pair with who? So potassium, this is where drawing your line to split up your ions really comes into play. It's why I was trying to get you guys to do that early on. Split them up. How do you split up Ki? Where do I draw my line? Exactly. The only place you can with that one. Where am I going to draw my line to my second compound? Right. So, this is where drawing your lines can help you out. So potassium is going to pair up with who in my other one? Nitrate, right? Because potassium is a positive ion. It can't pair up with lead. You can't have two cations in a compound. Just like you can't have two anions in a compound. So then iodine and lead are going to go together. But when we rewrite those, okay, it would be Ki. We'll talk about why it's Ki next period. And then plus PbI2. Right? The cations always come first. Now, why is it an I2? Because of the charge. What was the charge on lead? It was a lead 2. So we have to do our crisscross method. We're going to practice that more next period when we predict products. I'm sorry, I just rewrote that. That's what it should be. I got looking at the wrong thing. Everybody makes mistakes, man. It's okay.
Wait a second. No, that's what you started with.
Yeah, it should be KNO3. I'm just testing this. I'm just seeing if you guys are awake this morning. You know, we all thought we'd have a snow day. Now you're awake, Alex? Now you're awake? Yeah. There we go. KNO3, PbI2. So I was right with the PbI2 the first time. Oh, man. We all thought we were going to have a snow day. And joke's on us. Balance the equation. So, this other second one, this is where we have a strong acid with a strong base, and they're going to produce what we call salt and water. What's a salt? No, that is an example of a salt, but what is a salt? Nope. An ionic compound, guys. Any ionic compound is a salt. Balance this last equation. So it is already done. So again, this was a neutralization one. So, double replacement. The way I kind of think about this is that it's kind of the most complex. It's got two compounds that you start with, and it produces two different compounds. So if you see a lot of elements, chances are it's probably a double replacement reaction. Questions on the types? What I want, the last type we're going to talk about, guys, is combustion. Very briefly, we will come back and talk more about this when we do our organic chemistry unit. Basically, guys, a substance, and the substance that we use is called a hydrocarbon. So we'll talk more in depth about hydrocarbons when we get to organic. Basically, what does it sound like? What two elements are in it? Hydrogen, carbon, and that's really what they're made of. Sometimes they have oxygen in there, they can have a nitrogen, but it's mostly carbon and hydrogen. Okay? Yeah, be aware of it. We're going to talk, like I said, we're going to talk more specifically about it when we do our organic unit. But they release a large amount of energy and light and heat, or in the form of light and heat. You guys know what combustion reactions are. It's when everybody thinks of chemistry. What do you think was going to happen in here? Explosions. That's combustion right there. Okay? No thermite. No more. All right. So an example, guys, would be something like this. CX plus HY, or CXHY plus O2 yields, they always produce the same two products, carbon dioxide and water. Okay? Carbon dioxide and water. Where is the water? It's typically in the form of water vapor. Okay? So when you have a bonfire going, it's producing water all the time. Well, why wouldn't it put itself out? Because it's too hot. Okay, so it's water vapor, not liquid water. Now, why did I put X and Y there?
Because it could be any.
Yeah, they could be any different amounts of those guys. So, methane that we used the other day was CH4, so C1H4. That's going to change, okay, but the other pieces remain the same. That's how you identify a combustion reaction. All right, that's as much as we're going to talk about it right now. All right, I want you guys on this page in your notes to identify 1 through 10, and then we're going to come back and we'll classify these, and then we'll start talking about predicting products in the second period. So this is going to be one part of what you have to do on your test next week, is identifying the types of reactions. Now, why this is such a huge skill is what we're about to start doing, and that's predicting products. Okay? So you may be given, you will be given reactants, and you have to figure out what the products are and then balance the equation from there. Okay, so this is where it kind of, all of our naming rules that we've done back in Unit 5 really come into place. If you struggle with Unit 5, get in here and do the remediation. Okay, come and get the help if you know you struggle with naming. All right, here we go. So this is kind of our prediction process. You're going to be back, I believe, on the previous page in your notes. These are the steps that you need to go through for predicting products, and something we're going to do the rest of the school year. Jot these 5 points down. I'm going to kind of walk us through them, and we're going to kind of think about them as we do some practice. So step 1 is we're going to write the formulas. Now that's if applicable, meaning if you're given words, you've got to write the formulas. So they may give you formulas right away, and that, you can skip step 1. But we need to make sure that we use the crisscross method. This is something that people are too lazy to do. We can't be lazy. Okay? Number 2, once you have your reactants, you're going to identify your reaction type. What we just did on that practice sheet. You're going to classify the reaction. Number 3, you're going to split the compounds into their ions or identify your different pieces. Draw your lines if you have compounds. Then number 4, you're going to switch partners or break apart depending on the reaction type. And last step is balance the reaction. All right, so let's go through this. This is on page 9 in your packet. First one, we got to write the formulas. Well, do we need to write the formula here? Nope, they give it to us. So the second step then is to identify the reaction type. What type of reaction do I have here? Okay, could be synthesis, or single replacement, or what else? Which would be combustion. So those are the 3 types. How can we eliminate decomposition? Right, we have more than one reactant. We don't have one reactant. So we know it's not decomposition. How can we eliminate double replacement? We don't have what? 2 compounds, okay? So it could be combustion, it could be synthesis, and it could be single replacement. Now, really, can this be single replacement? Why not? Do we see, so oxygen is the element by itself, do we see that on our activity series anywhere? No, so we don't need to worry about that. So it's not going to be oxygen, it's not going to be single replacement either. So now it's combustion or synthesis. Well, It really could be one or the other, but given this, which one is it going to be? It's going to be combustion. Why? Right, CXHY plus oxygen. Now, one thing with this is not the only type of hydrocarbons. Again, we're going to spend more time on this when we get to our organic unit. But for now, this is what we're going to do. When we see that it's combustion, what products always form?
CO2.
All right, so there we go. CO2 plus H2O. So we start off with kind of an easy one. All you got to do is balance this equation. Go ahead and do it. So this is what this example would look like. Combustion reaction, it's carbon dioxide and water, and then just balance the equation. Let's move on to number 2. Okay? Oh, now what do we have to do with number 2? What's the first step? We've got to write the formula. So this is where we have to go back to our naming rules. Okay, so think about it. If there's prefixes, what do? Prefixes in a name, it's a molecular compound, so we just put those as subscripts. If there's no prefixes, what method do we have to use every time? Crisscross method. There we go. Barium. What's my formula for barium? Ba. All right. Plus copper 2 chloride. What does this Roman numeral 2 mean? What? Whose charge? Copper. Okay. So I've got Cu 2 plus. What's chloride's charge? 1 minus. Okay. So Cl 1 minus. Crisscrosses up. What's my formula going to be? Okay. Not difficult, right? You need to do that every time. Don't rush through it. If you do rush through it, if you can't balance the equation within a minute or so, you've probably done something wrong. Go back and look at your formulas. Did I do it correctly? Now, we got to identify what type of reaction. So we got our formulas. Let's start. What can we eliminate? Talk to me about what ones we can eliminate.
Double replacement.
Why?
Because there's not 2 compounds.
Okay, so it can't be double replacement because there's not 2 compounds. Somebody else. Hunter. Can't be decomposition. Why? 2 reactants. What else can we eliminate, Jill?
Single.
You sure?
Yeah. Barium's lower than chlorine.
But it could potentially be it, right? Okay, so it might be that because we have a single element. What else can we eliminate for sure? Combustion. Why?
There's no
Okay, and there's no oxygen, right. So in order to have combustion, you have to have oxygen, okay? But plus, like Cambria said, there's no carbon and hydrogen compound. So we can effectively eliminate double replacement, decomposition, and combustion. So now we're down to synthesis and single replacement. Well, which one do you think it looks more like from the examples that we have? What do we have here? So identify your pieces. Barium is a what? Element. So we've got an element plus, what is CuCl2? We've got an element plus a compound. Which one is it probably going to be? Think about if it was synthesis. Okay. What if it was synthesis? All of those would have to be together, right? So it would be something like barium, copper, chlorine, right? Does that make sense? Are we going to have 2 metals in a compound, guys? No. So if you think about it like that, put them all together, because synthesis, they'd all be in one. It doesn't look right. So which one does it have to be? Okay, single replacement. So barium is going to try to come in and kick out which one? You said what before?
Oh.
You said chlorine, right? But is not bromine. Is barium going to kick out chlorine?
No.
Barium's going to kick out who? Copper. Why? Because barium is a metal. It's going to kick out the metal or the cation, right? So, go to your activity series. Let's see if this will actually happen or not. I'm going to erase the ones that I already had. Okay. So, find barium. Barium's up here, 4th one down. Copper's where? All the way at the bottom. Side note, just take a look, guys, at the bottom. Look at your elements that are here at the bottom. What are those 2 or 3 at the bottom? Where do you find gold and silver?
In the little second stage.
Okay, but in real life, I'm saying. Where do you find gold and silver? In the ground, yes. Where's it used is what I'm getting at. What are some applications? What? Jewelry, okay, or a watch, something like that. Where do we use, or how do we use jewelry? Easy question. What? You wear it, okay, right? That's what I'm trying to get at. Does it react with your skin, guys? No, because Now, if you're allergic to it, yes, I get that. But for the most part, guys, gold and silver, they're so not active, and that's one reason why we use them as jewelry. Copper, all right, is a little bit more active than those two, but again, copper, you ever had the cheap jewelry where like it looks like it's silver, it looks like it's gold, but then after you wear it, it turns green? It's because it's got some copper in it. Okay, it could have some copper or some other things in there, but copper turns green. You guys saw that when you put it in the flame the other day. All right, so you get that idea, just a little side note. All right, so barium is more active, so therefore it will react. So our products now are going to be what? What element's going to be by itself? Copper, because it got kicked out. So Cu plus. Now, to write my new formula, I can't just assume that my subscript is going to be the same as it was for chlorine. Okay, it's going to be in this case, but go back to your crisscross method. 2 plus, Cl minus. This is the only time that we can change subscripts. When we're predicting products, we change subscripts. We may have to. They can be the same. They don't have to be. Balancing, we never change them. Only for predicting products will they possibly change. So here it's going to look at this. So it's going to be Ba, Cl2. Is this balanced? Yeah, it already is balanced.
Now, does it matter if you have BAC?
This has to be synthesis because it's two single elements. It's going to form a binary compound. So we've got to figure it out. We know we're going to have one product. Which elements are going to come first in that compound? Calcium. So what charge will calcium form? 2 plus. What charge will oxygen form? So when we crisscross those, right, it would be Ca2O2, but when we will reduce those down, CaO. What's the last step we have to do? Balance it. How are we going to balance it?
2 next to the CaO, 2 next to the Ca.
Just like that. Not too bad. I want you guys to do 4 and 5. So we know it's double replacement. Now, split your compounds up. Where am I going to draw the line in my first one? Right there. What about the second one? I'm not going to put my arrow up there now. After aluminum. Okay. So this may help you, and I encourage you guys to do this. Think about it like your FOIL method. Draw lines to show you who's going to pair with who. Now with double replacement, you've got a lot more to think about is what are their charges. Do we know the charge on? So we've got Pb, we've got chlorine, we've got aluminum, and we have nitrate. What ones do we know the charge for sure right away? Like it's not going to change. Aluminum is +3, chlorine's -1, nitrate is. Now lead, what do we have to look at to figure out the charge there? Chlorine subscript. So chlorine is a -1 times 4 is going to be what? Total of -4. What does lead have to be then to balance that out? Okay. Once you figure out your ions, it makes it a lot easier, guys, to write your new compound formulas. So aluminum and chlorine are going to go together. What's going to be my formula for that? Yep. Do you think it matters what order I put my new compounds in? No, it does not. Okay. What's my formula going to be for lead nitrate? Lead 4 nitrate. What's my last step I have to do? Balance it. How are these going to balance? So this is what this one will look like. Double replacement. Switch partners. Last one, CaCl2. What type is it going to be? Decomposition. So if they don't tell you how it's going to break down, you're just going to split it up into its elements. So what elements are we going to have here? Why is it Cl2? Brinkelhoff. Is it balanced? Yes. Look at that. Super easy. Some are going to be more challenging than others. Some are going to be easier than others. Questions? Your homework, guys, is page 12.